The process that we did earlier, where we're trying to figure out what is a good max depth value to use for a model, that's called hyperparameter tuning. We're trying to tune our hyperparameter, trying to investigate what's a good level to set for it, such that it's going to work the best. It's going to be the most general model as possible, a model that is neither underfitted or overfitted. I want to stress that max depth is a hyperparameter that belongs to decision tree. Other models have different hyperparameters, so don't expect to see a max depth parameter for a linear regression model or support vector machine. Different models will have different hyperparameters. It's important to understand what are the hyperparameters that a model has, because these are the things we can play around with, the things that we have control over to get the best model possible. Scikit-learn documentation tells you all the hyperparameters available for your model. In fact, if we look at our decision tree model, open up the documentation. We look at the parameters. These things are what are set prior. Sorry, these are the parameters that are set when we create an object from the class. So since they're set prior to learning, these are the hyperparameters. Remember, the hyperparameters are going to dictate the model structure, going to dictate the simple model parameters. So we see here things like that. So okay, yeah, here's our max depth value that we played around with. But we also see something called min sample split. It says here the minimum number of samples required to split an internal node. So the way that's going to manifest itself is if a node has less than the minimum number of samples given by min sample split, then the node isn't going to split. It's going to stop there. It's going to terminate right there. So playing around with this hyperparameter will also control overfitting and underfitting for our model. So let's play around with this hyperparameter. We can also tune more than just one hyperparameter at a time, and we'll go ahead and see that in a bit. So the process that we use to tune our model's hyperparameters is a bit tedious, right? We had to write a for loop and we had to generate results and see which one was the best to use. It's a bit tedious. So let's go ahead and see if we can encapsulate the entire process in a single estimator. So you might be tempted to say, okay, from sklearn, import sklearn base, import base estimator, and let's say regressor mixin or something like that, and say, okay, class, I'm going to construct a custom class to do this for us, to automatically do the hyperparameter tuning. I'm going to call it GridSearch, pass it base estimator, and regressor mixin, and then you say def init, and then you realize, wait a minute, what if scikit-learn already has something for us to use? What if scikit-learn already has an estimator that we can use to tune a model's hyperparameters? And in fact, it does, which makes sense because this is something we have to use for any machine learning workflow. We have to tune the model's hyperparameters. It's a common task, and it's going to be there in scikit-learn. So no need to construct our custom class here. Let's use the tools that scikit-learn is going to provide for us. Import GridSearchCV. This is the class. The model is going to do this grid search for us. Now, this GridSearchCV is an estimator. It's an estimator with a fit method and a predict method. So see how this works. So we're going to import GridSearchCV. We're going to create an object for our model. So we want to tune our decision tree regressor. So let's look at the syntax to work with GridSearchCV. We pass it the model, so this is what we want to tune. Then we also pass it a dictionary. We pass a dictionary that maps what are the hyperparameters we want to tune and what are the hyperparameter values we want to investigate. So we say here, we want to investigate max depth. We want to control what's a good max depth value to use, and we're going to investigate the following range, from the value of 1 all the way to 14, since remember Python uses inclusive exclusive convention. And we're also going to play around with this min sample split hyperparameter. And we're telling scikit-learn, specifically GridSearchCV, investigate values of min sample split anywhere from 10 all the way to 110 with spacings of 10. So let me illustrate what's going to go on here. So open up a whiteboard. So what's happening is that it's going to construct a grid based upon the hyperparameters you passed it. So we said here max depth of 1 to 14. So we say 1, 2, 3, 4, 5, not Johnson scale 6, and so forth, all the way to 14. So this axis represents max depth values. So max depth value of 1. The other hyperparameter we want to tune is min sample split. So we say range from 10 to 110 of 10 spacings. So this represents 10 here. This represents 20. This represents 30. So it's constructing a grid. And you can go ahead and fill it all out. This keeps on going all the way to 100. So it constructs these grid of all the pairs of max depth and min sample split. And then what it's going to do is going to brute force and try out all these sets of hyperparameters. In this case, just 2. Figure out what's a good pair to use for max depth and min sample split. Hence the name grid search. It's going to construct this computational grid. Now with grid search, you're not restricted to a 2-dimensional grid. You can have a 1-dimensional grid. Perhaps there's only one hyperparameter you want to tune. Let's say we only want to tune max depth. Then in our grid search, we would pass a dictionary with only one key value pair. We can pass more than 2 key value pairs. In that situation, it's going to construct a sort of n-dimensional grid to investigate, to brute force through and figure out what's a good combination to use for our model. Now let's look at this keyword argument we use, CV equals 5. So CV stands for cross-validation. So we're using a 5-fold cross-validation strategy. All that means is that if we have our training data, let's say this is our training data here, we're going to construct multiple folds with our training data. So let's, for example, let's say we say 3 folds. I know we show 5 folds, but just for illustrative purposes, let's say if we chose 3 folds. That means we're going to create one group of observations, call that fold 1, another fold, call it fold 2, and the last fold, call it 3. These are equally sized folds. And what it's going to do is that grid search is going to take one grid, one point from the grid it constructed. Let's say the first one is max depth value of 1 and min sample split of 10. It's going to train a model with max depth of 1 and min sample split of 10 with the combined folds 1 and 2 and test on 3. Then it stores the error metric of interest. Then it's going to do the same thing, but train on folds 2 and 3, test on 1, record the error metric. And then do the last combination of train on the combined folds 1 and 3, but test on 2. And then it derives and is going to calculate the average across those 3 folds. And then it repeats the process for all the sets of hyperparameters you've passed via that dictionary. So that's what it means by it's going to use a k-folds cross-validation strategy. In this case, we use 3 folds. The example here we set to 5. It's customary they use anywhere from 3 to 10 folds. So sometimes people so this will vary. Of course, if you use more folds, your training time will be longer. But the nice thing about using more folds is you're less susceptible to randomness. Remember, you're taking the average across the metric, so if you have a large sample size, the more confident you can be in your answer. This other keyword argument, njobs equal to 2, this process here of grid search can be done in parallel. So if we have sufficient memory, you can go ahead and set njobs equal to 2. So if you have 2 parallel jobs. You can also set njobs equal to -1, which will use all processors you have for your computer. Now sometimes it's tempting to set njobs to a high number, but you might run into memory issues. If you're working on the mini project and you're running into memory issues, perhaps you shouldn't do a large number of jobs. Just set njobs equal to 1. This is the scoring criteria we are using to pick the best model, the best of hyperparameters for our model. Another keyword argument that I like to use is verbose equals 1. And this will tell you, if you set verbose equal to 1, when we use a grid search, it will print out what's going on. So it's a nice way to update you of what's going on through this process. Sometimes this can take a while, so it's nice to see a report of what's going on and what's figured out, since we know it's working, and we can kind of estimate how long it will take to finally run. Now, GridSearchCV is an estimator with a fit method. So when we invoke fit of this grid search object, what is happening is going to take this data, it's going to apply this k-folds cross-validation strategy I described, using all the sets of hyperparameters that you construct, that it's constructed based upon this past dictionary. And then once it's done that, it's going to use the best model. It's going to use the model with the best set of hyperparameters. So there you go. So we see we have 140 candidates, 5 folds. Tells you the number of fits, how many times it has to invoke fit. Okay, it looks like it took about 8 seconds. After we've trained the model, this grid search model, there's an attribute called best params, which is a dictionary that tells us what were the best hyperparameters. So it says the best set of hyperparameters that I found, or that grid search found, was that we should use a max step value of 9 and a min sample split of 100. Now notice there's 140 candidates. Well, that makes sense, because if we look at here, these are 14. There's 14 values in this iterable, and here there are 10 values in this iterable. So 14 times 10 is 140. So those are 140 candidates it must search through. It must investigate. Brute force itself, all those 140 candidates, apply this 5-folds cross-validation. So a total of 170 fits. Okay. So now what we can go ahead and do is, with that grid search object, there's a best estimator attribute which will return the best estimator. Will return to you the model that was the best, that investigated. So this model here has been trained on the full data set with a max step value of 9 and a min sample split value of 100. So let's go ahead and train that model there. Although we don't have to do this. In fact, we can go ahead and use, every time we use the predict method of a trained grid search object, it's automatically going to use the best model. But sometimes you don't want that that grid search apparatus tied to the model. So you can go ahead and just pull out the best model via this attribute. So let's fit the model. Let's go ahead and plot it, see how well it works. Let's visualize the results. And there was our best model.